previous lessons, we talked about all the benefits to displaying data using different forms of display, like histograms have their place, whereas dot plots we use for other things. So one of the things that is really good about a scatter plot is it can be used to show a correlation. A correlation is a relationship between two variables. So you can see when you look at a scatter plot, does one of these values tend to correlate with the other? Can we see what's going to be expected and use that to make predictions about what's going to happen in the future? So a positive correlation means that as a value of one set of data increases, the other data will also increase. It also goes the other way. As one goes down, the other goes down, but they move in tandem. They move at the same direction. So for example, the amount of rain would have a positive correlation with the size of the puddles. The more it rains, the bigger the puddles get. The less it rains, the smaller the puddles get. You think about a place in a park that always has this one big puddle, but the less it rains, it starts to shrink until it eventually goes away. A negative correlation means that the value of one set increases, the other data value will decrease. So an example of negative correlation would be the age of a watch and its battery energy. The longer you have your watch, the lower the amount of energy left. So it's not necessarily a good thing or a bad thing, it's just that the two values go in opposite directions. Another option is that a relationship may show no relation between the variables. In that case, we would say that they have no correlation. An example of no correlation could be the temperature in Alaska and your grade in math class. We live in Georgia. How cold it is in Alaska has no bearing on how you do in your math class. So those would have no correlation if I were to plot that data. All right, so here's an example of what those would look like. A positive correlation is going to end up with a cloud of ordered pairs that as you move from left to right, they are increasing. So it's getting higher and higher. So another example of positive correlated variables would be the time spent studying and a student's grades. The more this kid studies, the higher the grade would be expected to be. So it's not a perfect correlation. It just means that we would expect if a student studied a bunch of hours, we would expect to see their grade up higher. It would be weird if we had a kid who had studied for 5 hours and they had, a 0 on a test. Of course, it happens, but it's outside of the norm. A negative correlation will look like this: the amount of time spent training and the time it takes you to run 100 meters. We're in track season right now. So the more time you spend training and practicing, hopefully the quicker you run the 100-meter. So if I train every day, then my 100-meter time will be a lot quicker than if I don't train. No correlation. Again, it's fun to think of things that are not correlated. The colors in the rainbow, the number of colors in a rainbow that you can see, and your shoe size. They're not really related at all. Okay, so scatter plots help us to see correlation between bivariate data. However, it's important that you know that it doesn't equal causation. Just because two things are correlated, it doesn't mean that one of them is causing the other. It just means that there's some relationship. So for example, the amount of time you study for a test would have a positive correlation with your grade. However, the study time alone doesn't cause your test score. It's not causing your score to go up, because then you would never have that kid that I talked about that studied for hours and hours and still bombed the test. There are lots of other factors that go into your test score, so that keeps it from being a true causation. The chart below gives another kind of silly example. It says the number of people who died by becoming tangled in their bed sheets correlated with cheese consumed. Okay, so as you can see, the more cheese that's consumed, the more people die from getting tangled in their bed sheets. That doesn't mean that eating cheese causes you to die from bed sheet tangling. I don't know what the reason for that is, but there's probably not a causation. I hope not, because I like cheese and I don't want to die from getting tangled in the beds. All right, so in addition to being classified as positive or negative correlation, we can also classify correlations as weak or strong. So if a relationship is really, really close between two variables, then you're going to have a really strong correlation. Correlation is given from on a scale from -1 to +1, and we call that the correlation coefficient, and we use the variable r to represent it. So the stronger a correlation, the closer it will be to 1 or -1, to the absolute value of 1. So it kind of makes sense. If it's a positive correlation and it's a really strong positive correlation, then it's going to be close to 1. If it's a really strong negative correlation, then it'll be close to -1. A weaker correlation is going to be close to 0. So a weak positive correlation will be like 0.1, 0.01, something like that. A weak negative correlation, -0.1, something like that. Okay, so if the relationship has no correlation, the correlation coefficient will be 0. So r will equal 0 in that case. Unless you have a calculator or computer, you have to estimate correlation coefficient. Later we'll show you how to find them using a calculator, but the math used to do correlation coefficients by hand is way, way above Algebra 1, so you're not ready to do that yet. This illustration here can help show, though, how you would estimate a correlation coefficient for a given scatter plot. So in this one, you have ordered pairs that are forming almost a perfectly straight line that is going up. It's increasing as you go from left to right. So that is definitely a positive correlation. And because it's perfect, we would say this has an R of 1. Over on the other side of things, we have a negative slope. It's decreasing as you go from left to right, but it's still a perfectly straight line. So this would be an R of -1. Then here you have a high positive correlation. It's definitely forming a line. I could draw myself a line that goes up here, but it's not quite perfect, so they say R is 0.8. This one, still positive, because if I were going to draw a line that kind of went through these ordered pairs, it would go something like that. So it's increasing, but the dots are kind of all over the place, so they estimated it to be about 0.3. On the negative end, they have similar things. I've got this one would be a line that is negative, but it's not perfect, nor is my line perfect. So we have R is -0.8. This one is pretty weak correlation because my dots are kind of spread out all over the place, but it's going down, so we're going to say -0.3. This one right here, those are just a cloud of dots. They're just kind of all over the place. I could not really use that to make any good prediction, so we would say this has no correlation, which means the correlation coefficient is 0. Okay, so describe the correlation between the age of a car and the value of a car. Well, if you think about, you always hear when you buy a car off the lot, it loses a huge percentage of value as soon as you leave the lot. We did all those exponential decay problems that said as a car ages, it loses, 8% of its value every year. It depreciates in value. So that would be a negative correlation because as the age of the car goes up, as it gets older, the value of the car goes down. Now, this is assuming we haven't gotten into, an antique or anything like that. But we would say it's a negative correlation. Okay, my next example says determine if the following relationship is correlation or causation. So, remember, causation means it's actually causing one thing to happen. And correlation means that they kind of go together. So, the number of firefighters at a fire and the size of a fire. Does the number of firefighters cause the size to get bigger or cause the size to get smaller? So, the instinct would be to say, yeah, if I've got a bunch of firefighters there, then the fire's going to get smaller because that's what they're there to do, is make the fire get smaller. But again, remember correlation. It's definitely going to be correlated because if more firefighters show up, then the fire gets smaller. But is it truly causation? Are the firefighters, the very existence of the firefighters, making the fire get smaller? If I'm a firefighter and I come to a fire and then I just stand there and look at it, is it going to get smaller? No, because I'm not magic. I'm not making the fire get smaller just by being there. I'm doing things to make it get smaller. I'm spraying it with the water. I'm, doing whatever. I don't know what firefighters do. They fight the fire, but they do something that's causing the fire to go down. Also, there are things like, if the fire just naturally burns itself out, if it's a brush fire and it's not spreading like a wildfire, but it just finishes, then that's going to end, even if no firefighters show up. So I would have to say that this is correlation. I can see an argument for causation, but really there are other underlying factors. And that's the thing you've got to think about that differentiates between correlation and causation. If there are other factors at play, if it's not just a firefighter shows up and poof, the fire gets smaller, then it's not causation. All right, you guys go ahead and try a couple, and then I will see you for the next video. Bye.